Boker Tov. That's pretty much my readings in Hebrew for today. I'd like to talk today about some synergies that exist between natural gas and oil shale in Israel. We've heard most of the morning on tremendous natural gas supplies in the Levant Basin. And now I'm going to talk about the other side of the energy equation, the liquids that are needed in order for transportation fuels and military purposes, and how the natural gas and the oil shale work together to supply this energy security. So the outline of the talk will be first a review of the oil shale resources in Israel, and then the process for developing them that I worked on for over 30 years at Shell, called the in-situ conversion process, and then the synergies between the natural gas and the oil shale. So what is oil shale? Basically, oil shale is a sedimentary rock, and it contains solid hydrocarbons called kerogen. Simply put, it's a source rock that hasn't been buried deeply enough and gotten into the oil expulsion window. So it's what we call an immature source rock. Over geological time, you have to reach a window between 70 centigrade and 170 centigrade, and that's over millions of years. But if you heat it up in the subsurface over a period of a few years, you have to reach temperatures of the order of 300 degrees centigrade. And at those temperatures, you'll generate hydrocarbon liquids as well as gases. This slide shows the global distribution of the unconventional resources in the world. Unlike the conventionals, where there's about 1 trillion barrels that we know of left in the ground, the unconventionals really haven't been tapped yet. There's about 12 to 14 trillion barrels of known resources. There are two types, the heavy oil shown in yellow and the oil shale shown in blue. The size of the circle here is logarithmically scaled, so a circle this size is 100 billion barrels. For contrast, a 1 billion barrel oil field is considered an elephant, very, very large oil field, very rare. And here you can see that the unconventionals dwarf the conventionals. Another good thing about unconventional resources is that you typically know where they are. The exploration risk does not exist, but they're much harder to get out of the ground, so the production risk is greater. If we look at the oil shales of the world, the largest oil shale deposits are in the United States, in the Colorado, Utah, Wyoming area. And there's about 1.2 trillion barrels in this oil shale. The second largest oil shale deposits in the world are in Israel and Jordan, together over 800 billion barrels. Israel alone has conservatively over 250 billion barrels, making it equal in magnitude to Saudi Arabia in terms of its proven reserves. The Israeli oil shale deposits are of late Cretaceous age, deposited about 70 million years ago, very similar to the Jordanian sister deposits of the time. And as shown in this slide, the very largest of these deposits is located in the Shvila Basin. The oil shale in place, as I said, is about 250 billion barrels. That's a very conservative estimate. It's actually probably considerably greater than that. And the main deposit in the Shvila Basin has the majority of that 250 billion barrels. You can see that there are other deposits in Israel that we're much more familiar with, those in the Negev region. These tend to be very small deposits. They're thinner, they're not as rich. Typically, these deposits are at the surface and are mined, whereas this very, very large Shvila deposit is subsurface, about 300 meters of overburden, and therefore you need a technology that can produce it without mining operation. And it's these type of deposits that the in-situ conversion process works so well on. If we look at on a seismic map on the top of the Judea group, you can see in green here the synclinal structures where the oil shale deposited during the Cretaceous period. You can see the acreage that IEI has a license on over here, 238 square kilometers. It's located not too far from Ashdod, so it's very nice with respect to the Maridia and the Tamar platform bringing natural gas ashore. We're only about 25 kilometers from Ashdod. And we're located very nicely on the various crude pipelines and that go from Taifa to Ashdod to refineries in the country, as well as a products pipeline that goes down to Eilat. So Israel is very well positioned for oil exporting. It can export both to the Mediterranean, which would supply, for example, Europe, and it can export also through Eilat, the Asian market. The hydrology of the Shvila Basin has been studied extensively. Basically, coming off the Judean hills, you have the aquifer, the Judean group. Then you have an aquiclude, which is the Menucha and the Mishash formations. Then the oil shale, which is the Gara formation. The Tekiya, which is a clay marley stone, another very good aquiclude. And then you get into the Eocene rocks. The target of the oil shale in situ development would be right in the middle of the Gara formation, leaving over 250 meters of aquiclude to the aquifer. These are both extremely tight rocks, and we've cored them and measured both the permeability as well as the hydrology in the wells, and we are convinced that these are two extremely tight aquicludes. Now, let me back up for 1 second. But it's not just that these things are aquiclude, it's that the aquifer is strongly confined. And the pressure in the aquifer is greater than the pressure that we will operate the process in the oil shale. So even if these weren't, even if there were clumps or fractures that ran through this, the water would go this way instead of oil shale products going down into it. So you have belt and suspender situation here. This is what the Shvila oil shale looks like. Extremely uniform and very rich. This is a deposit that's world scale in terms of its richness and magnitude. Here's the Fisher assay from our Aderet well. The Fisher assay is the standard method of determining how much oil will be expelled on pyrolysis of the source rock. And you can see that we've got about 300 meters of oil shale. The middle 100 meters is what's called the high-grade zone. This high-grade zone is over 25 gallons a ton. And you see exactly that same high-grade zone in Jordan in the oil shale deposits that Shell is working on there. All told, you have an average of over 200 meters at over 20 gallons per ton. So this is a world-class resource that's in the same range as Colorado. Now, the in-situ conversion process basically involves heating the oil shale in the ground using conventionally drilled oil and gas wells. The wells are equipped with heaters. They can be drilled either vertically or horizontally, but of course in Israel, because you want the very smallest footprint, you drill horizontally. And the other advantage of drilling horizontally is if you have a a high-grade zone like this one here,